Independent and dependent events have to do a lot with what we talked about in class. We're going to make some tree diagrams in a second. But independent and dependent are exactly what they sound like. If two events are independent of each other, that means that the first thing doesn't affect the second thing. Dependent events, the first thing does affect the second thing and the thing after that, on and on. So here's some examples. Are the results of flipping a coin and rolling a number cube independent or dependent? Well, on a coin you can get heads or tails, and on your number cube you can obviously get 1 through 6. It does not matter what you get on your coin, you still have options 1 through 6. And it doesn't matter what you get on your dice, you still have heads or tails to choose from the coin. So this is independent of each other. Next one, a box is filled with a mixture of jelly beans. You and your friend both like grape. You pick one out, and then your friend picks one. Are these probabilities independent or dependent? Well, if you have a bunch of jelly beans and your friend takes a grape one, that means that you can't take that grape one too. So his choice, or your choice, you pick first, your choice affects his choice. He has less to choose from. So those two events are dependent. C, a coin is flipped and then flipped again. Are the flips independent or dependent? So this one, we're using the same coin over and over again, but it doesn't matter how many times you've gotten heads in a row, you can still get heads or tails the next time around. So these two events, even though they're the same thing, same coin, are still independent of each other. So here is another probability tree. The combined probability of two events happening can be shown with a counting tree or an area model. So if we're flipping two coins, our first coin, coin number 1, we have options heads or tails. And then coin 2, we have heads again and tails again. And then let's say you got tails the first time around, your two options for coin 2 are still heads, or you could get tails. So our outcomes could be head-head, head-tail, tail-head, or tail-tail. Those are the only possibilities that we have. And then this area model kind of does the same thing. These are a little off. If you get a heads on the first one and a heads on the second one, you get HH. If you get tails on the second one and a head on the first one, you get HT. And then here's HT or TH, however you want to write it. And then this one is TT. So now that we can come up with all the outcomes, let's think about probabilities. We found some probabilities today after making our counting tree, but we can kind of do that before, or we can do it with our counting tree. So same counting tree that we have right here, and our probability of getting a heads or tails on the first one is 1/2, 0.5. And then it doesn't matter what we got on the first one, we still have a 50-50 chance of getting a heads or tails on the other one. So each of their probabilities are 0.5. Same thing if you get heads or tails on the first one, you get 0.5 of a chance for heads and 0.5 of a chance for tails. So that means that we have 4 possibilities. Any specific outcome has a possibility of 1 out of 4, or 0.25. And to get that, all we need to do is multiply the probability of getting the first thing to happen times the probability of getting the second thing to happen. And here, the same thing. You have 4 spaces in your square. Probability of getting like 2 heads, there's only one option out of 4. So the probability of combined events is found by multiplying the probability of the component events. So let's do some more problems. What's the probability of spinning 2 reds in a row? Well, the probability of getting a red on my first spin of this spinner over here is, there's 1 red space, and it's kind of cut into fourths, and red occupies 2 of those fourths. So that means the probability of getting a red the first time around is 1/2. Now, it doesn't matter that I got a red the first time around, because if I spin this again, the probability of getting another red is still 1/2. And if I multiply those two things together, it tells me the probability of spinning 2 reds in a row is only 1/4 or 25%. The probability of spinning a green first and then a blue. Well, a green one has a probability of 1/4. And since it's independent, I can spin it again. It doesn't matter what I get the second time around. I can get a blue and it still has a 1/4 chance of landing on blue. So when we multiply these together, we get 1 out of 16. There's a 12.5% chance that I'm going to get a green one and then a blue one. C, combining all these together, what's the probability of spinning a red first and then a blue? Well, a red first, I have a 1/2 chance. And then a blue one, I have a 1/4 chance. So if we multiply these things together, I end up with a 1 in 8 chance of landing on a red first and then a blue. So it's higher than landing on a green and then a blue because red takes up more space. D, what's the probability of spinning 3 greens in a row? Well, the probability of getting 1 green is 1/4. The next green is still 1/4. And then the green after that is still 1/4. So if you multiply 4 times 4 times 4, we end up with 1/64th chance of getting 3 greens in a row. It's a pretty small chance, which makes sense when you think about it. Landing 3 greens one right after another when it only takes up 1/4 of the space is not very likely. So all of these events right here were independent of each other. It didn't matter what I spun on the spinner. When I spin it again, I still have those 3 options. I still can get blue or green or red. One's not taken out or used up. If 2 events are dependent of each other, their combined probability must take into account the effect of the first event on the second. So we're going to do an example just using these 4 cards below, all the aces in a deck of cards. So if I pick a card at random and keep it, and then my friend picks a card at random, those 2 events are dependent on each other. If I pick out the ace of diamonds, my friend cannot pick out the ace of diamonds. She doesn't have that option. So the problem asks us to find the probability that I will pick the ace of diamonds and my friend will pick the ace of spades. So for me, if I pick out the ace of diamonds, there's only one of those out of the 4 cards here. My friend wants to pick out the ace of spades. Again, there's only one of those cards, but remember, I picked this one out. So my friend has a 1 out of 3, the 3 that are left, this one, and this one, to pick the one that I want, the ace of spades. And then we multiply them together just like before. So 1/4 times 1/3 gives me 1 in 12 that combination is going to happen. Let's do another one. What's the probability that I will pick a red ace and then my friend will pick a black ace? So if we go back to our deck of cards here, I want to pick a red ace. So out of the 4 aces there, 2 of them are red. And then I want my friend to pick a black one. So I picked either this one or this one. My friend has 2 options for black aces. The ace of spades and the ace of clubs. So there's still 2 options. But this time, remember, my friend only has 3 cards to choose from because I took 1 out. So this time the denominator changes, but the numerator stays the same. So we can multiply these together just like before. We'll get 4 on top out of 12. And this is something that can be reduced, so we should reduce it to 1/3. This one has a greater chance, a much greater chance of happening than me and my friend picking out specific cards. So 1 out of 3 times that we do this, I'm going to pick a red one, my friend will pick a black one. So this sums up the two different probability when we're combining events. If they're independent of each other and I want A and B to happen, you just multiply their probabilities together because one doesn't depend on the other one. But if they are dependent on each other, that means that I want to pick A first and then B. There has to be a specific order to them, and one is going to change the outcome of the other one. You take the probability of your first one, probability of A, and then multiply that by the probability of B after A has happened. So in this card problem up here, this is the probability that A happens, and this one's the probability of B after A. Because now we only have 3 cards to choose from instead of 4.